So this is a talk about some work that I did together with Gregory Maleka and some other colleagues at BlueRock Security. This is formerly Bedrock Systems. And this work was done in around 2020, 2021, but I think is still relevant to the SCL4 community. And in particular, I'm trying to now understand more about SCL4 as well, to understand whether some of the userland verification work that we've done could potentially be ported to microkernels like SCL4 and tools like MicroKit. And in particular, what I'm going to talk about is what we call protocol-based verification of device drivers in concurrent separation logic. And the high-level idea is we really think about, which I'll get into in a bit, the device and the driver you can think of as two separate threads, and a natural way to and one is a hardware thread, one is a C++ thread in our case, and they're running concurrently to each other. So a natural way to verify that setup is to use concurrent separation logic. So that's what I'll talk about. This work all took place in the context of the following sort of system stack. We used a different microhypervisor in this case, not SCL4, but an L4 style microkernel. And this is written in C++. We implemented a number of userland components on top of Nova, a terminal multiplexer, a virtual machine monitor, VirtIO-based virtual networking between virtual machines, and also device drivers. And that's going to be the focus of this talk, as I said. I'll draw some examples from our verifications of a PL011 UART and a ZynqMP DMA device driver. All of this software was written in C++. So one of the things that we did at BlueRock was to implement a program logic, a concurrent separation logic for C++ using Iris. And that program logic is open source at the link above. The automation is still proprietary, but the program logic itself is open source. So at a high level, we think of device drivers according to the following sort of cartoon picture. The driver implemented in C++ uses memory mapped I/O to perform control operations on the device, and also sometimes to read data from device registers. The device has registers like control, data, and flags, and also maybe some internal state, like FIFOs or IRQ state. And the device can interact with the world via I/O pins, I/O wires, or DMA. And it can send interrupts, so signals back to the device, back to the driver. So this is the high-level picture of how we sort of think of devices and drivers. And just as a very small example, here's a picture of a UART where registers might be control and data registers. We might have state for transmit and receive FIFOs, and then also state for interrupts. And then this UART device can send characters and receive characters from the outside world. All right, so I just want to introduce, before I get too far into the talk, our notion of protocol-based driver verification. And as I said before, the idea is to think about the driver and the device as two separate threads in concurrent separation logic. So the device is a hardware thread, or it might be multiple threads, potentially, multiple hardware threads, that might be clocked independently from CPU cores. And the driver is one or more threads implemented, in our case, in C++, running on CPU cores. As I said at the beginning of the talk, I think a very natural way to verify drivers is to think about, to use concurrent separation logic to think about the driver and the device as two separate threads that interact via some sort of concurrency protocol. And I'll show you what that looks like in a moment. In particular, one way to think about this is we want to establish a protocol between the driver and the device that sort of characterizes properties about the current device state. So what we're going to do is we're going to build a protocol, which you can think of as a concurrency invariant, that talks about properties of the current device state. And the driver is going to control this protocol, and we're going to show that the device respects this protocol in certain ways. And in particular, you can see on the right-hand side of this slide, devices can respond to things like MMIO operations, but they can also do things like take steps independently of the driver. So a UART could read a character from a wire, which is something that the driver didn't ask it to do, but it will load that character into a FIFO to be read later, let's say. So one of the things that we need to show when we establish a protocol between the driver and the device is that this protocol doesn't overly constrain the device. So the device needs to be shown to sort of be consistent with the protocol in a certain way. And I'll talk about some of those details in just a moment. And in particular, one of the things I want to talk about over the course of the rest of the talk is that it's kind of weird to think about a device as a thread in a concurrent separation logic, because there's no program there, right? So we need some way to sort of embed the device into the program logic. So that's the first thing that we're going to do. We're going to embed the device into the program logic. And I'm also going to talk a little bit about how we specify MMIO operations, because that's a very interesting part of the spec, I think. Then I'll talk a little bit about protocols and give some example protocols for a UART and DMA device. And then finally, I'll try to draw out some SCL4 connections. One of my goals of coming here is to learn more about SCL4, and I am hoping to talk to people afterwards over the course of the conference to sort of better understand ways in which things like MicroKit and other parts of the SCL4 ecosystem could be exposed for use in iris-based logics. And talking to Matt definitely would be useful as well, given the talk he just gave. Okay, so I said the first step is we need to embed devices into the program logic. There's sort of 3 sub-steps here. We're first going to build an operational model of the device. So this is just a standard small-step operational semantics. It's derived from documentation of the device and also litmus tests on the device. And this gives you sort of a small subset of a model of a UART. You can see that there's a state type that models things like the receive and transmit buffers, some IRQ state, and things like that. And then we're going to have an operational model that has steps for each of the things that the device can do. So respond to a MMIO operation, an MMIO write to the data register will be specified in the way that's given on the bottom right hand of the slide. All right, so this step is tedious and somewhat error prone, I think, but essentially we build an operational model of the device as best we can from the documentation and from interacting with the device using unit tests. And I think here's one place, speaking of connections to work done in SCL4, in the SCL4 community, to the extent that we can share these sorts of models, I think it would be absolutely wonderful. Because as I said before, there's a lot of work that has to go into, this is just a small part of a larger model, and a UART is itself a very simple device. But when you get to things like NICs and DMA devices, things get more complicated. Not to mention like interrupt controllers and all sorts of things. Okay, so the next step is going to be to use ghost states. This is something that Matt mentioned. Iris has a notion of ghost state for talking about things that aren't actual program variables, let's say, but things that are abstract. So gamma on this slide is a ghost location that's going to contain conceptually the state of the device. And what we're going to do is we're going to use something called the Iris authoritative camera to build 2 assertions that allow us to talk about the state of the device from 2 perspectives. From the perspective of the driver, so state.frag on the left is the sort of driver's view of the state, and state.auth is the device view of the state. And auth stands for authoritative, so this is sort of, you can think of this as like the real state of the device, and frag is the driver's view of the device. And we want these 2 things to be consistent with each other. And in particular, there's some algebraic laws that describe how this ghost state interacts. So if you have ownership, so star here is star in separation logic, and consistency says that if you own both the fragmentary view and the authoritative view, that implies that the 2 views are consistent with each other. Otherwise, the star would not hold. And then you can also update this ghost state in a particular way. So if you have both of these views of the ghost state, you can update the state to some new state under a sort of ghost update modality. And now here, this new state, new underscore st, is sort of arbitrary. Now we don't want the state to be arbitrary in general. We want it to be a state that's actually one reachable via the device operational semantics. So we'll get to that point in a second. But this is sort of the algebraic view of this ghost state. And then the final thing that we do is we build an invariant to hold the ghost state. In particular, so we build this thing at the top in the sort of dotted box is an Iris invariant that says there exists some state, this is the state of the device, such that state.frag gamma st holds. And conceptually, the authoritative view of this state lives with the device. But because we're doing a driver verification, we're going to use the driver's sort of view of the state of the device primarily. So that's what we're going to stick in this invariant. And now we have all of the ingredients to sort of specify what it means to perform an MMIO operation. So let's say the driver wants to write to a device register via an MMIO. So the driver is going to initiate a change to the device state via an MMIO operation. The sort of informal contract between the driver and the device in this case is that if the driver can show that for whatever the state the device happens to be in, if this MMIO is safe for that state, so the device can actually respond to that MMIO operation, then the device guarantees to update its state in such a way that it's consistent, its new state is consistent with the MMIO write event that was sent. So this is the sort of informal contract that we use to specify an MMIO write operation. And MMIO reads and all sorts of MMIO operations are sort of, to whatever register you're interacting with on the device, will have a similar sort of flavor. So here's what this spec looks like formally. And all of the details here are not super relevant, but essentially the same sorts of driver obligation and device obligation pieces fit into the formal spec as the ones that I showed you on the informal spec. So this AU thing is a device from Iris called an atomic update. It allows me to specify this MMIO operation as sort of higher order Hoare triple style that says that if the driver can show that it owns the state, possibly a state.frag assertion on the state of the device, possibly by opening some invariant, and the driver can show that the write to that register is safe, then the device is going to do its update to its operational model using this device step operation, which is the device operational semantics. It's going to produce state.frag of some new state st prime, and then we're going to learn some Q as a result of all of this stuff that happened. So there's a lot of details on this slide and some Iris-specific stuff, but the high-level idea, as I said before, is that the driver has an obligation, needs to show that the write that it's trying to perform on the device is safe, and the device has an obligation in return to actually take a step according to its operational model and return a new device state as a result of this operation. Okay, so that's MMIO, and we talked about how we embedded devices into our program logic, and then we're able to specify MMIO as a result. But now we need some way, so like previously we said, okay, the driver needs to show that this MMIO is actually safe for the current device state, but our invariant had a completely sort of arbitrarily existentially quantified state. So we need some way to sort of specify what kind of state the device is in. So to give you an example, let's say you're building a driver for a UART, you might have an arbitrarily sort of uninitialized state initially, and then you put it in an initialized state where you set the baud rate, you set other stuff like that. That's going to allow the UART to actually take steps, like read characters from the wire and stuff like that. So we need some way to sort of specify those sorts of protocols over the state. So we're going to introduce, as I said before, a sort of protocol over the state that you can think of as a high level as a state machine. But formally, it's sort of a set of invariants that are going to hold on the state of the device at different points in time. So in the UART example, we have an initialization invariant that holds up until the point at which the UART can start sending and receiving characters. And then we have a steady state invariant that governs the state of the device while it's able to read and write characters. So the driver is sort of going to control when we move from one state to another, from initialization to steady state. We're going to have to show that the device respects this invariant, or this set of invariants. And the invariant, or the invariant that holds the protocol at a given time, is going to sort of characterize properties of the state ST that formerly was sort of arbitrarily existentially quantified. So we're going to be imposing new properties on ST using this protocol. So here's an example picture of the DMA protocol for our ZCU 102 DMA device driver. And there's essentially three states. There's an idle state, a working state, and a done transaction state. And this is a simple mode driver, so it doesn't use scatter-gather buffers. And so it's a little bit simpler in that case. And essentially, the driver, when it wants to start a transaction, it's going to move the device from the idle state to the working state. The working state is going to contain all the resources necessary for the device to perform a copy, a memory copy. Then the device is going to finish the transaction, interrupt the driver and say it's done, and then the driver will move the device back to the idle state. And just to give you a flavor here of I realize I'm going a little bit fast, I think. To give you a flavor of the kinds of invariants we need to build for driver verification, this is an example of part of the working state invariant for our ZCU102 DMA proof. And essentially, I'll just point out a couple interesting things here. This is a predicate and separation logic. And these things in the sort of brackets here, these are pure properties about various variables mentioned in the predicate. We also have things like ownership assertions here for the memory that the device needs to access in order to perform copies. And essentially what this predicate says is that the DMA device is somewhere in the middle of a copy. So this is the invariant that will hold all the way from the beginning of a copy to the end of a copy. And at the end of the copy, this invariant will imply, together with some other facts, that the copy was actually performed. And in particular, we're copying from some source pointer containing some bytes L to some destination pointer D pointer, which is sort of starred together with D pointer containing the rest of the space that we're going to copy into as the transaction proceeds. Okay, so one of the things I said previously is that, okay, when we establish one of these protocols over the device and over the interaction between the driver and the device, the driver controls sort of which state of the protocol we're in, but the device needs to respect the protocol. So what does that mean? Well, we're not doing a proof of the device because it's not a program in C++ in our program logic, but it's embedded as an operational model in our logic. And one thing that we don't want to happen is we don't want to impose an invariant on the state of the device that prevents the device from taking steps that it needs to take. So, so one thing that could go wrong is that this invariant that we build for our DMA device might not have enough resources to allow the device to actually take steps to perform a copy. So this would sort of be a bad situation that we want to prevent. So what we're going to do is we're going to impose an additional condition on the protocol that we've defined, which we call, it's sort of a generic name, we call it compatible. So the predicate, or the series of predicates that form our protocol are compatible with the device if they don't block the device from taking steps, and if whatever step the device takes from the state of a given state that satisfies a given protocol stage, will sort of bring the device back into that predicate. So there's this additional condition compatible interp P. P is the phase of our protocol, like idle or working state. Interp P is an interpretation of that protocol stage as a predicate in separation logic. And compatible over some predicate over states in separation logic says that, okay, for any state inside that predicate, if that state satisfies the predicate, then WP step holds for that state and the invariant. And what that means is that the device is, whatever step the device is about to take, it's safe, or there is at least one step that the device can take, so it's a safe state. And whatever step the device takes brings the device back into the invariant. Okay, and WP step here, I don't have the definition of that in the slide deck, but you can think of this as, so it's derived from the operational model of the device. It's the weakest precondition predicate transformer semantics derived from the device semantics. And there's a picture of what's going on the right hand of this slide. You can think of interp P, this is like the predicate that holds for a given point in the device's operation, and we want to make sure that the device's steps are safe and the device can never exit the invariant. Okay, so why do we build all of these pieces? Well, they seem somewhat complicated and somewhat disconnected potentially. Ultimately, we want to prove sort of reasonably straightforward high-level specs and separation logic for our device drivers. So I want to give you an example spec for a device driver for a PL011 UART. This is the spec for reading a byte from the UART, and it's a function that takes an out parameter, so that's this argument here, and the intention of this function is to read a character from the UART into the out parameter. And it's specified using a predicate that we derive on top of the operational model called intrace, which is sort of the predicate the trace of all the characters that have been received by the UART so far. And the way to interpret this spec is to say that, okay, R is the return result of this function. If, and that's could be an error, it could be no error in this case, E none. If R equals E none, then there exists some C in the input trace of the UART. And this is you can think of it as the input trace containing all the characters that we know that the UART has received so far. And out contains that 8-bit integer C as well. So this is sort of a trace level specification of a read function on a UART, which is derived from all of these pieces that I've showed you so far in the talk. So we verified a ZynqMP DMA driver as well, and this is a simple mode DMA driver, so it doesn't use, as I said before, scatter gather buffers. And this, you can think of a DMA device essentially as allowing you to perform memory copies. So this is essentially what this spec says. There's some source pointer containing some bytes this is a permission Q and then bytes L. And then a destination pointer, D pointer, containing some uninitialized, potentially uninitialized characters. And if the result of this function returns E none, then D pointer will contain the same bytes L that we started with in the source pointer. And this little 1 here to the left of the L, which looks a lot like an L, is the permission. So this means like write permission to the destination array, if that makes sense. Okay, so all right, and here's where I love to talk with people more about potential connections. So I talked about this protocol-based verification concurrent separation logic of device drivers. When I was at BlueRock, we used a program logic for C++, and verified not just device drivers, but parts of a virtual machine monitor and parts of a vSwitch and a UMX, a terminal multiplexer, and a bunch of other things as well. And so we have BlueRock has a lot of verification tools built around concurrent separation logic. And I'm very interested in understanding whether things like MicroKit in the SEL4 ecosystem could be exposed to userland verification in concurrent separation logic. So if we can build specifications of MicroKit interfaces in such a way that proofs in concurrent separation logic could use those, I think that would be very nice. I've read a little bit about some of the driver work, and there will be a talk actually later in the program on Pancake, which is a new language for device drivers and verification built on top of SEL4. There may be some connections there, and I'm very interested in learning more as well. So I think I'll stop there. That's okay. Yeah.
So you said in the beginning or somewhere in the first part that the tedious bit is actually, well, one of the tedious bits is coming up with this operational model for the device.
Yeah, yeah.
I was wondering if you had some sort of automation there. I mean, you said it's a combination of specs and litmus tests.
Yeah.
Do you have thoughts on like automation? I don't know, generating litmus tests from your specification or something along those lines that would maybe make this slightly less tedious?
Yeah, I mean, I think the operational models that we built as specs for devices weren't executable, which makes it harder to generate litmus tests from them. But I think if you built executable specs for devices, then it would be very nice to be able to use those to test, directly test against devices without having to write litmus tests by hand. Yeah, but our process was typically use the documentation provided to try to write an operational model based on our own understanding as well. And then for parts of the device that were unclear, litmus test to try to resolve those sort of small pieces, if that makes sense.
But all manual at this point?
But all manual, yeah.
If you had a question, you wrote a test that.
Yeah, but definitely building executable models and using them to test automatically would be very interesting and good. Yeah. Yeah. Yeah.
How does the connection on the other side, like between the client and the driver, looks like? Just the same
Yeah, I mean, the general framework concurrent separation logic allows us to reason about concurrent threads, like concurrent C++ programs, for example. But I don't know necessarily, and the same principles like the kinds of invariants in ghost state that are used, that I presented here, they were principally used by Iris folks in the context of concurrent program verification. So I think those techniques apply. Whether this particular protocol-based approach that I described works exactly the same way for concurrent C++ programs or C programs, probably not directly, but like a lot of the ideas are transferable, definitely. And I think most of the inspiration for trying to do this way came from, concurrent program verification. And our thought was, okay, how do we take the device? And the reason about the device is just another party in this sort of concurrent protocol. I don't know if that helps, but.
Yeah, I was just more interested in the protocol between the client communication and the driver, like that side of communication.
Yeah, so you mean a client calling the driver? Yeah, I mean, you can either call the driver sequentially, or you could set up a protocol where it sends requests to the driver over a concurrent FIFO or something. I think either of those, those sorts of things could all be done. But that's sort of out of scope of the driver verification, I think.
So apparently you sort of assume that the client call is more like sequential.
Say it one more time? No.
Is the current client call to the driver more like in a sequential way? If you do a driver verification?
So like this function memcopy or read byte, we assume that they're called by, I don't know if this function is necessarily reentrant, for example. Like you'd have to show, you could prove that multiple threads could call this simultaneously, potentially, but the way to do it would be to figure out how to split up the resources in separation logic in the precondition such that multiple threads could call the function. And I don't know if in this case that would be possible.
One more question.
Yeah.
You had a trace predicate for the characters received by the
Yeah. Yeah.
Do you sort of more generally reason about traces of events? Is that the way you kind of specify systems? Or
yeah, so I mean, the way we did it in this case is we took the device operational model and then built sort of a model on top that tracked the history. And then we exposed this predicate as using ghost state. So it's somewhat one-off in this case, but I think that model could be done. Using traces to specify systems makes a lot of sense, though, more generally, too. All right. Thank you.